After dealing with infinite limits, there are some famous indeterminate forms like 1 power 0, 1 power infinity, 0 power 0, infinity power infinity, like that. Out of all those things, the form 1 power infinity has a peculiar shape. What I mean to say is, suppose a limit like limit as x tends to a f of x whole power g of x is given to us, which actually takes the shape of 1 power infinity. That is, limit as x tends to a of f of x is 1 and limit as x tends to a of g of x is infinity. Infinity. 1 power infinity. Then what can we say? What can we say? This is nothing but e power limit as x tends to a f of x minus 1 into g of x. By usual simple manipulation, we'll be able to have this. Okay, if the given indeterminate form does not take the shape of 1 power infinity, if it looks like 0 power 0 or infinity by infinity, then you convert that expression by using either applying logarithms or by simple simplification techniques, so that L'Hospital's rule can be used. But for 1 power infinity, if it takes the shape 1 power infinity, then it can be simplified by using e power limit as x tends to a of f of x minus 1 into g of x. Into g of x. Into g of x. Let us now observe one such problem. Look here. What do you say about this? As x tends to infinity, this tends to 1 and that is infinity. It looks like 1 power infinity. We can simplify this as e power limit as x tends to infinity x square plus 5x plus 3 by x square plus 3x plus 2 minus 1 into x. F of x minus 1 into g of x. So that it is e power limit as x tends to infinity of x square plus 5x plus 3 by just considering the LCM. You cancel x square, 5x minus 3x is 2x, 3 minus 2 is 1, so it is 2x plus 1. 2x plus 1 into x is 2x square plus x. Limit as e power limit as x tends to infinity, 5x minus 3x is 2x, 2x into x is 2x square, 3 minus 2 is 1, 1 into x is x, 2x square plus x by x square plus 3x plus 2. 2x square by x square is 2. So the limit of this expression as x tends to infinity is 2. Hence the answer is e square. By using that technique, rather methodology, we could have used e power limit as x tends to infinity f of x minus 1 into g of x. Well, my dear, this is not the question of solving this problem. How to generalize this result? If both numerator and denominator are quadratic expressions with leading coefficient as 1, that is coefficient of x square is 1, the answer will be 5 minus 3 is 2, e square. Now you tell me, this is 15. Tell me the answer. e power 12. This is 8. Tell me the answer. E power 7. E power 7. And let me now try to generalize this. Limit as x tends to infinity, x square plus ax plus c by x square plus bx plus d whole to the power of x. How can you simplify this? It is just nothing but a power a minus b. A power a minus b. Not only this problem, so many problems as and when it takes the shape 1 power infinity, they can be simplified. The limits can be evaluated by using that formula, rather methodology, e power limit as x tends to a of f of x minus 1 into g of x. We have seen, we have enjoyed how easier it is to use it. Likewise, we use the indeterminate forms and the other forms also. In general literature, what do you mean by continuity or continuation? A regular flow without any break. A regular flow without any break. The word which is meant in that way has been introduced in mathematics. What is the purpose of introducing it? If a particular function is continuous, then its graph will be a smooth curve without any breaks, jerks, peak points, sudden change of direction, like that. They will not be there. We mean it. Well, how to understand it? How to understand it mathematically and according to the principle systematically? We shall now think of. Actually speaking, continuity is a local point, local character at a particular point only. Just like the types of functions, 1 function, non-2 function, constant function, like that. Is the function 1 meaningful question? Is the function on2 meaningful question? Is the function continuous? Incomplete question. You must say, is the function continuous at that particular point? That is a meaningful question. Okay, let me try to illustrate this with the help of an example in our daily life. Suppose we are riding on a bike on a highway. Assume that there are some 3 speed breakers at regular intervals, say for half kilometer or 1 kilometer, like that. If there are no speed breakers, our journey will be continuous. At those speed breakers only, definitely the continuity of the journey will be broken. Either the speed might be reduced very well, or it may happen for you to stop at that instant, like that. The continuity of the journey will be broken. Otherwise, the journey will be smooth. If there are no such obstructions, the journey will be continuous. Imagine this consequence in the case of functions also. You observe the graph. What do you observe? The continuity of the graph has been broken at this point. You observe another graph. Yes, of course. If you consider this as a wave, say, in physics, the particles are not in the same phase of vibration along this and along this. Yes, of course, the direction has been suddenly changed at this peak point. At that peak point. So continuity of the graph is broken at this point. It is discontinuous at this. One more. Observe this graph of signum function or sinem function, that is mod x by x. It is 1 if x is greater than 0. It is 0 if x is 0. It is minus 1 if x is less than 0. The continuity will be broken at this point 0. Isn't it? So, it has been split into two parts. One more thing. Absolutely discontinuous at particular instant. Moreover, in all these graphs, observe the nature of the graph here in this region. There is no obstruction, there is no jerk, there is no jump, there is no cut, or there is no any peak point here in this region. In this region, the function is continuous. In this region, the function is continuous. But here it is not continuous because it has been broken. This is continuous. This part, the function is continuous. By understanding these graphs or looking at those graphs, we must be able to know or learn that continuity is a local character of a function at a particular point or a particular region. It is not the name of a function. That is why in the beginning we have said, is the function 1, 1? Meaningful question. We can test. There is a mechanism. Is the function on 2? Yes, it is a meaningful question. We have a mechanism. We can test. Is the function continuous? Not incomplete question. Is the function continuous at x equal to 1? It is a meaningful question. Suppose this is the point x is equal to 1. At this juncture, there has been a break for the graph. Clearly the function is discontinuous at this region or x, at the point x equal to 1. Whereas suppose this is half or 0.7 or something. Here the function is continuous. Therefore, it must be spoken of, it must be understood, it can be thought of as a local character only. Continuity is a local character of the function at a particular point or a particular region, around the particular region. This is the meaning, pictorial meaning or the conceptual meaning of the continuity. And let us now look at the practical part of that, the definition, the concept, like that. Let us have the brief, concrete part of the definition. As we could have just discussed, continuity of a function is a local character at a particular point of the domain. At a particular point of the domain. Let f be a real function. What do you mean by a real function? A function whose domain and codomain are subsets of real numbers. If only domain is a subset of real numbers, then it is termed as a function of real variable. If only codomain is a subset of real numbers, then it is called a real valued function. If both the domain and codomain are subsets of real numbers, then it is termed as a real function. Such a real function is there. Let f from S to R be a function. Where this is the explanation of the word real function. As subset of real numbers or entire real numbers, it's a function. Well, let small a belong to domain of S. The domain of S. Moreover, A must be an interior point of S. What do you mean by an interior point? What do you mean by an interior point? It is just enough to understand that if you go in detail of that concept, it will be an ocean. We cannot go into the details of that. Let us understand the word interior point. And look here, let this be S. Let this be the point A. If there is a neighborhood around A which is entirely contained in S, then A is an interior point of S. Then A is an interior point of S. Isn't it? Look here. Can this be an interior point? No, it's not an interior point. A belongs to S. Not only that, there is a neighborhood, at least one neighborhood around A which is entirely contained in S itself. That is the nature of that. That is the nature of A. In that sense, we say that A is an interior point of S. If to every epsilon greater than 0, there exists delta greater than 0 such that x belongs to A minus delta to A plus delta implies f of x belongs to open interval f of A minus epsilon to f of A plus epsilon. That is, x belongs to A minus delta to A plus delta. What does it mean? Mod x minus A less than delta implies mod f of x minus f of A less than epsilon. This looks like the conceptual definition of limit of a function. You can recollect. Of course, in the definition of limit, 0 less than mod x minus A less than delta. There, x is not equal to it has been restricted. But such restriction is not available here. Mod x minus A less than delta means x can take the value of A or value A also. I just do not mind. And in the place of L of the limit definition, we have f of A, mod f of x minus f of A less than epsilon. If this happens, then we say that f is continuous at x is equal to A. So this sentence reveals us that the continuity of f is a local character at a point A of the domain. It must be a point of the domain first of all. Yes. If to every epsilon greater than 0, we could have already discussed with the existence of delta corresponding to epsilon, which are supposed to be very, very small positive real numbers, such that x belongs to open interval A minus delta to A plus delta implies mod f of x belongs to f of A minus epsilon to f of A plus epsilon. And equivalently to say, for all those points around the neighborhood of A, their images, that is f of x's, should lie in the neighborhood of f of A, that is f of A minus epsilon to f of A plus epsilon. And it is possible to express in terms of modulus symbols also. That is, whenever mod x minus A less than delta, mod f of x minus f of A is less than epsilon. This is continuity of f. Let us now try to have the pictorial meaning of this sentence. How can we explain this? Let us now see the graphical explanation of the definition of continuity. Well, let us observe the graph drawn on the board. This is the function y is equal to f of x. A is a point of the domain of f, that is f of A is surely defined. What can you say? What can you see? What can you observe from this diagram? For all those x's which lie in this neighborhood, for all those points in the neighborhood A minus delta to A plus delta, what is the care of address for the images of such x's? You observe f of x's will move like this, like this, like this, like this, like this. The t's, they lie in the neighborhood f of A minus epsilon to f of A plus epsilon. Anyone can say very easily that x belongs to open interval A minus delta to A plus delta implies f of x belongs to f of a minus epsilon to f of a plus epsilon. This is the direct, simple, very clear meaning of the definition. It can be viewed directly from the graph itself. If such things happen, if such a thing happens, then we say that f is continuous at x is equal to a. Continuous at x is equal to a. Well, while solving some numerical problems, construction of this delta, consideration of epsilon, all these things may be time taking. Therefore, we revise this definition as a brief set of conditions as follows. Yes, we follow that. In the next consideration, we'll be going to give the set of conditions to say whether a function f is continuous at x equal to a or not. Yes. A real function f is continuous at the point x is equal to a if and only if, number one, what could we have planned? What is our motto? We do not use either epsilon or delta or modulus or any other thing. What is the brief way of listing out the conditions, set of conditions to say that whether a function f is continuous at x equal to some point, say x equal to a, which is supposed to be more helpful for us in solving numerical problems. The first condition is f of a is defined. That is a basic condition, isn't it? That is a basic condition it is. F of a must be defined. A must be a point of the domain. A must be a point of the domain. Previously we have thought as an example, we are riding on a bike on a road, a highway on which a speed breaker is there. Is the function is our journey continuous at that speed breaker? Meaningful. The speed breaker lies on the road. There is a highway, we are riding on that. There is a small lane just beside us here. Is our journey continuous at this point? Foolish question. Our journey is being done on the highway. If at all to discuss any continuity, it must be done on the highway only. So, in order to discuss the continuity of a point, the point must belong to the domain. That is, f of a must be defined. That is the meaning of the first condition. Well, second condition. Limit as x tends to a of f of x exists. A limit of f of x as x tends to a must exist. Well, why does this step has come into fray, has come onto the picture? While going through the definition of continuity itself, we could have recollected the definition of limit of a function. In the definition of limit of a function, in the place of L, we could have had f of a. First of all, limit must exist, and that limit must be f of a. How can you grasp that? By looking at the theoretical definition of continuity. That is, of course, the third condition. Limit as x tends to a of f of x is equal to f of a. If these three conditions are satisfied, then we say that f is continuous at x equal to a. You can say, for the sake of fun, like this: to win the match, quarterfinals, semi-finals, finals. If a particular team loses at the stage of quarterfinals, it cannot think of semi-finals and finals. That is, if f of a is not defined, on the spot itself we say that it is discontinuous at x equal to a, that is not continuous at x equal to a. Suppose there are some functions for which first condition is satisfied, second condition is not satisfied. What does it mean? A team in a particular tournament is qualified in the quarterfinals and entered into the semi-finals, but it loses the match in the semi-finals. What does it mean? Can it think of finals? No, it goes to the home. Like that. First condition is satisfied, but second condition is not satisfied. Then also we say that the function is not continuous at x equal to a. There might be some functions for which first condition is okay, second condition is also satisfied, but third condition will not be satisfied. That is, we can compare this with the situation that there is a particular team in a tournament which is qualified in the quarterfinals, which is qualified in the semi-finals also. It has entered the finals, but it loses the match at the finals. Then also it is discontinuous because it has lost the match. Like that. So, in order to test the continuity, this is the order that one must follow. The first condition, f of a must be defined. Second condition, limit as extends to f of x exists. Third condition, limit as extends to f of x is equal to f of a. Of course, these three conditions again can be put in a box in still more a brief way. What is that way? Let us now look at that brief way. F is continuous and x is equal to a if and only if f of a from left is equal to f of a This is a briefcase and this is a suitcase. According to the necessity, we follow to use the conditions. You see, in this step, f of a is used. It means that f of a is defined. F of a from left and f of a from right are used. It means that those two do exist. Is equal to is there. It does mean that limit as extends to a f of x exists. And it is equal to f of a. Third condition is also satisfied. Therefore, this is the brief way of explaining the rule that must be satisfied by a function f to say that it is continuous at x is equal to a. That is why, humorously, I like to speak, this is a suitcase, but this is a briefcase. That's all. Yes, let us now look at the situations where to use suitcase or briefcase. Let us see some more examples. Look here. Observe the question. F of x is equal to 1 by x minus 2. We all know that the function f is defined with the domain r minus singleton 2. It is not defined at x is equal to 2. That is, f of 2 is not defined at all. So, imagining the suitcase conditions, the very first condition f of a is defined is failed here. So, the function has been not qualified in the quarterfinals itself. No question of considering its limit or equality. So the first condition is a failure condition here. Therefore, is not continuous at x is equal to 2. Well, let us see another example. F of x is equal to sine 1 by x if x not equal to 0 is equal to 0 if x is equal to 0. Is f continuous at x is equal to 0? He is asking. Observe the problem. F of x is sine 1 by x if x not equal to 0. And it is 0 if x equal to 0. What is the question he is asking? Is f continuous at x equal to 0? X equal to 0. What is the point of continuity he is asking us? He likes to inquire of. He likes to inquire of the continuity at x equal to 0. Well, let us follow the list of conditions. What is the first condition? F of 0. Is it defined or not? Yes, of course. What is f of 0? 0 is defined. Okay, it has been qualified in the quarterfinals. Well, now we shall look at the second condition. What is the second condition? Limit as x tends to 0 of f of x. What is limit as x tends to 0 of f of x? Limit as x tends to 0 of sine 1 by x. In our earlier discussions itself, we could have stated that the limit does not exist. This does not exist. Observe there, the first problem, first condition is not satisfied. In the second problem, first condition is okay, but second condition is not satisfied. Therefore, this function is not continuous. Not continuous. F is not continuous. If a particular function is not continuous, we say that it is a discontinuous. Discontinuity and not continuous are meant in the same way. Now, let us observe the third condition. F of x is equal to sine x by x if x not equal to 0, 0 if x is equal to 0. Is f continuous at x equal to 0? Observe this question. Observe this question. What is the point of continuity he is asking us? X equal to 0. In the list of conditions, what is the first condition to be verified? F of a, that is f of 0. Is it defined? Yes. First condition, okay. F of 0 is 0. What is the second condition? What is the second condition? Limit as x tends to 0 f of x. Limit as x tends to 0 of sin x by x is 1. Oh, happy, it is defined. For this one, f of 0 is equal to 0 is defined. First condition is satisfied, verified rather. The second one, limit as x tends to 0 of f of x. What is f of x actually? Sin x by x. As x tends to 0, its limit is 1. So it is 1. Second condition is also okay. What about the third one? Value of f of a which has been obtained in the first condition. Value of the limit which has been obtained in the second condition must be equal. Are they equal? It is 0 and this is 1. They are not equal. Therefore, third condition is failed here. All the three examples you can look at a glance on the board. The first problem, first condition is not satisfied. That is why it is not continuous. In the second problem, second condition is not satisfied. Second condition in the sense limit as x tends to a or x tends to 0 of sin 1 by x is not existing there. Second condition is not satisfied. That is why we say, rather we have said that this is discontinuous at x equal to 0. And here, first condition is okay, f of 0 is defined. Second condition is okay, limit of f of x as x tends to 0 is existing, 1. But the third condition is failed. So it is discontinuous at x equal to a. So for x equal to 0, it is discontinuous or not continuous. So far, we have seen 3 examples respectively in which the first condition is satisfied in the first problem, is not satisfied in the first problem, second condition is not satisfied in the second problem, third condition is not satisfied in the third problem. Now let us explore one more example in which all the 3 conditions are satisfied. How can we say that? How can we do? Observe the function, rather the problem. The function given here is f of x equal to 1 plus x 1 by whole power 1 by x if x not equal to 0. Is y if x is equal to 0. He is asking us the continuity at x is equal to 0. What is the point of continuity? 0. There is in the place of a, we have 0. What are the conditions? First condition, f of a must be defined. What is f of 0? F of 0 is e. Oh, happy, it is defined. First condition is verified. Okay. Second one. What about the second one? Limit as x tends to 0 of f of x. What do you say about it? Does it exist or not? Let us see. This is equal to. We notice that there is one of the standard limits, it is equal to e. We now should feel happy because the third condition is also verified. That is, this is e and that is also e. Therefore, f of 0 is equal to limit as x tends to 0 of f of x. Third condition is also okay. For such functions, we say that f is continuous at x is equal to 0. We have come across 4 different problems in which the first condition is failed in the first problem. Second condition is not satisfied in the second problem. Third condition is not satisfied in the third problem. And all the 3 conditions are satisfied in the fourth problem. In all these 4 problems, we have followed 3 conditions. That is, in our humorous way of the previous discussion, we could have used the suitcase, but not the briefcase. What is that? We shall now use that in the next coming example. Let us consider the function f of x is equal to 1 plus x square if x greater than 0, x square minus 1 if x less than 0, 0 if x is equal to 0. Again, he likes to ask us the continuity of the function at x is equal to 0. What is the question? Is f continuous? Well, to test the continuity, we have had 3 conditions in our mind. The first one is f of a must be defined. The second one is limit of f of x, etc. To find the limit here, we are given the nature of f of x in both the regions to the left of 0 and to the right of 0. So, here it is convenient for us to use the briefcase conditions as we spoken of humorously. According to them, the first one, what is f of a from left? That is f of 0 from left. What is f of 0 from left? What is the meaning of f of 0 from left? Limit of f of x as x tends to 0 from left. From left. Who is left? To whom? X is left to 0. X is left to 0 means x less than 0. This is the function. So f of x as x tends to 0 is 0 square minus 1. What is that? Minus 1. Next one, f of 0. Is it defined? Of course. At x equal to 0, it is 0. F of 0 from right, the third one, the right hand side limit, it is 1 plus 0 is 1. What can you say here? Therefore, f of 0 from left is not equal to f of 0 is not equal to f of 0. Perfect negation. What is your opinion? Is f continuous at x equal to 0? Never. Almost all the conditions are dissatisfied here. Therefore, the function is not continuous at x is equal to 0. Not continuous at x equal to 0. So, now I like to change some things here. I have changed the function. What is the fate of this function about the continuity at x is equal to 0? As usual, what is f of 0 from left? Left hand side definition, 1 minus 0 square is 1. Second one, in that brief case, the first item is f of 0 from left, second item is f of 0, third item is f of 0 from right. We like to calculate those three in an order. The first one is 1. Second one, what is f of 0? It has been redefined here in this problem. I have changed the problem. You see, this is 1 but not 0. Hence it is 1. F of 0 from right, that is right hand side derivative, 1 plus x square. What is 1 plus x square? It is also 1. Therefore, here f of 0 from left so it has turned us to a continuous function at x equal to 0. All the three values have become equal. F of 0 from left, f of 0 and f of 0 from right, they are equal. Therefore, we declare that the function f is continuous at x equal to 0. Is continuous at x is equal to 0. Good, next. Just like one-sided limits, now and then we look at one-sided continuity also. What does it mean? Now let us have a look over that. F of a is defined limit as x tends to a from left of f of x exists. Limit as x tends to a from left of f of x is equal to f of a. If these three conditions are satisfied, then f is continuous from left at x is equal to a, or f has left continuity at x is equal to a. This is what we say about left continuity. For continuity, we recall that there is a set of three conditions. The first condition is f of a is defined, no change in the condition. In the second condition, in the main definition, full limit must exist. For one-sided continuity, that is for the left continuity, left-hand limit should exist. It's enough. Third condition, that so-called left-hand limit which is existing must be equal to f of a. If these three conditions are valid or rather verified, then we say that f is continuous from left at x is equal to a. Or in another way, we express it as f has left continuity at x is equal to a. Both are meant in the same way. There is no any particular symbol to represent the same. Moreover, in a briefcase model, that is f of a from left is equal to f of a. That's all. That full briefcase has been broken. The first part is only considered to say that f is continuous from left and x is equal to a. Okay, one can easily trace the plan of explaining the right continuity also from this strategy. We could have explained ourselves about the left continuity now. Can we explain the same at the right hand side? That is, can we give the meaning for right continuity at x equal to a? Why not? We can. How? Observe this. First condition, no change. Second condition, like this. Third condition, that's all. If you speak of left hand limit only, then it is corresponding to left continuity. If you speak of right hand limit only, it is corresponding to the right continuity. So that f is continuous from right, we say. From right, x is equal to a. Or right continuity at x equal to a. Then this condition changes. It is quite evident, it is quite clear that f is continuous at x equal to a if and only if it has both left continuity and right continuity at x is equal to a. It must have both left continuity and right continuity at x equal to a. Then only we will be able to say that f is continuous at x equal to a. Yes. Let us observe some examples for one-sided continuity. Observe the function f of x equal to 2x plus 3 for x less than 1 is 5 for x is equal to 1 and 3x minus 2 for x greater than 1. In three different regions the function has been given. Therefore, let us test the continuity with three different parts. That is, by the way, what is the question actually? Is f continuous at x is equal to 1? That is the question. Let me first calculate f of 1 from left. What is the left hand limit? X tends to 1 from left. X lies to the left of 1. That is, x is less than 1 must be considered. So this is the definition that must be used here. 2 1s are 2, 2 plus 3, 5. F of 1 is 5 directly from the definition itself. And f of 1 from right is 3 1s are 3, 3 minus 2, 1. What is your observation? Left hand limit exists, f of 1 exists. These two are equal but not equal to f of 1 from right. So from these two conditions we say that from these two itself we say that f is continuous from left or right? From left, because left hand limit is becoming equal to f of 1. So f has left continuity at x is equal to 1. Likewise, we can create so many problems also in which it is continuous from right but not continuous from left. This is what we say about one-sided continuity. It's not impossible. We can create, look here, 2x plus 3 for x less than 0 is equal to 5 for x is equal to 0. I have changed the question. You observe. F of x is equal to 2x plus 3 for x less than 0 is equal to 5 for x equal to 0 and 5 minus 2x for x greater than 0. He is asking about the continuity of the function at x equal to 0. So what are the things that must be found here? f of 0 from left, f of 0, f of 0 from right. What is f of 0 from left? So zeros are 0, 0 plus 3 is 3. F of 0 is 5. Here itself we say that the function is not continuous at x equal to 0. In particular, f is not continuous from left. It is not possessing left continuity. Let us check about the right continuity. What is 0 from right? 5 minus 0 is 5. As of course, our plan is successful. We could have constructed a function which has right continuity. As from these two, we notice that f has one thing is very clear. If a function has both left continuity and right continuity at a particular point, it is surely continuous at x equal to that point. And if either left continuity fails or right continuity fails, we say that the function is discontinuous at x is equal to that point. Observe the graph here. How smooth it is as a curve. It can be called a smooth curve. There are no breaks, there are no jerks, rather jumps or peak points, sudden change of directions. No such things are observed here. It is continuous at every point of the domain. It is continuous at every point of the domain. Such a function is said to be continuous on the domain, or continuous everywhere on the domain. If this is the domain, f is continuous on S. F is continuous on S. That is, if f from S to R is continuous at every point of S, then we say that f is continuous on S. F is continuous on S, or simply f is everywhere continuous on S. There is nothing wrong in saying that. Instead of that, it is just enough to say that f is continuous on S. Now, of special interest is the case when the domain of the function is a closed interval a to b. What happens? If f from closed interval a to b to R is a function, then f is continuous on AB. You may say, just now we have discussed, if a real function f is continuous at every point of the domain, then it is continuous on the domain S. Here also the domain S, instead of S, we are writing closed interval a to b. Therefore, f is said to be continuous on closed interval a to b. F is said to be continuous on closed interval a to b if and only if it is continuous at every point. There lies the problem. At A and B, can you anticipate the full continuity? No. Why? Because to the left of A, not included in the domain. So at A, at most you can anticipate right continuity only, because the region to the right of A is only involved in the domain. Similarly, at B, you have no meaning at all to the region to the right of B. It is not involved, rather included in the domain. So you can expect, that is, you can anticipate the continuity, only left continuity only at x equal to b. Keeping all these things in view, this sentence is said in the form of a definition as, number 1, f has right continuity at x is equal to a, because the region to the right of a is only involved in the domain. Second condition, f has left continuity at x is equal to a. And the third one, f is continuous at every point of open interval a to b. That is, between a and b there is no exemption. It must be continuous at every point there. At a there is an exemption. It need not be continuous from left. It cannot be. Why? Because the region to the left of a is not involved in the domain. Similarly, at b there is an exemption. What is that exemption? It is just enough if it is continuous from right at x is equal to b. That is, it has a right continuity x is equal to b. Yes, if these three conditions are satisfied, then at that particular instant, for the case of that such functions, we'll say that f is continuous on closed interval a to b. And the set of all such functions is denoted by set of all continuous functions like this on closed interval a to b. If you write f belongs to this, then f is continuous on closed interval a to b. Of course, this symbol is not included in your syllabus. It is just enough. If you can know that, that is omit it.